So, how does an AI go from just seeing letters on a page to actually getting what a sentence means? It's a huge leap, right? Well, today we're going to dive into that journey. We'll look at the key breakthroughs that taught machines not just to read words, but to really understand them in context. All right, so let's get right into it. The whole thing really boils down to this one massive question. How in the world do you take human language, which is, messy, creative, and just full of nuance, and translate it into something a computer can understand? Because at the end of the day, a computer only speaks one language, numbers. And that was the first huge hurdle to overcome, turning these abstract ideas, these words, into cold, hard numbers. This is, and I can't stress this enough, the absolute foundation of what we now call natural language processing, or NLP. So, the big solution that came along is this idea called word embedding. The easiest way to think about it is like giving every single word its own unique numerical fingerprint. It's this process that finally lets a computer start to see how different words relate to each other. So now, a word like king isn't just King to the machine, no way. It becomes a specific point, kind of like a star in a giant multidimensional galaxy of words. And its location is defined by this long list of numbers, which we call its vector. And of course, queen gets its own unique spot, its own vector in that same galaxy. Okay, and this is where it gets absolutely wild, seriously. These vectors, these number lists, they capture meaning in a way that feels like pure magic, or maybe mathematical poetry. You've probably heard this one. If you take the vector for king, subtract the vector for man, and then add the vector for woman, the result you get is a new vector that is almost identical to the one for queen. I mean, come on. It shows that these incredibly human abstract ideas like royalty and gender can actually be represented and manipulated with just math. It's just brilliant. But of course, that wasn't the end of the story. This incredible breakthrough led to the next big problem. See, these early models gave every word just one fixed meaning, one vector, no matter how you used it. And as any human knows, language is way, way trickier than that, right? I mean, think about a super simple word like bank. Are we talking about a place you put your money? Or are we talking about the side of a river? To us, it's a no-brainer. We get it from the context. But for an early AI, this was a massive, massive roadblock. So in these first-generation models, the word bank had just one single numerical fingerprint, one vector. That means whether you said, I need to open a bank account or I'm sitting on the riverbank, the AI saw the exact same thing. And you can imagine the confusion that caused. The next big leap forward was creating what we call context-dependent embeddings. This is where the AI finally learned to look at the words around the target word. So now, the bank in bank account gets a totally different vector than the bank in riverbank. At last, context was king. And this fundamental need for better context, well, it set the stage for one of the biggest revolutions in the history of NLP. A brand new type of model that could understand language in a way that was starting to feel a lot more human. And that model was BERT, dropped by Google back in 2018. Now, the name sounds a bit technical, bidirectional encoder representations from transformers, but it really does tell the whole story. Transformers are just this powerful AI architecture for handling sequences like sentences, but that first word, bidirectional, that's the secret sauce. You see, older models read a sentence like you'd read a ticker tape, one direction, only looking at the words that came before. But BERT reads bidirectionally. It looks at the whole sentence at once, the words before and the words after a target word, simultaneously. This gives it this incredibly rich, deep understanding of context, a lot more like how we humans actually read. So how did it learn this trick? Well, it was through this super clever training method that's basically a giant game of fill in the blanks. I'm talking billions of sentences where a word was randomly blanked out or masked, and BERT's only job was to figure out the missing word. Now, to get good at that, you have to understand the full context, right? What came before and what came after. And let me tell you, it got really, really good at it. Okay, so the models are getting super fluent, they're understanding context, and then a new kind of spooky problem starts to crop up. They got so good at sounding right that you wouldn't notice when they were completely wrong. And this is the now famous problem of hallucination. Just look at this. On the left, you ask who was the first person on the moon? The AI says with total confidence, Charles Lindbergh. I mean, the grammar is perfect, the sentence structure is flawless, but the fact is just wrong. Or on the right, you ask it to summarize a recent article, and it starts pulling in info from over a decade ago. In both of these cases, the AI sounds super convincing, but it's totally disconnected from reality. So when you hear people talk about LLM hallucinations, and LLM just stands for large language model, this is exactly what they mean. It's any time the AI gives you an answer that sounds totally plausible, looks great, is grammatically perfect, but it's just factually wrong or nonsensical. And this problem can rear its head in a few different ways, right? It could be just making up facts, using out-of-date information, maybe even citing sources that don't exist. Or sometimes it's just a subtle inaccuracy that's hard to spot. It's a huge, huge challenge if we want these AIs to be trustworthy. So what's the fix? How do you stop an AI from just making stuff up? Well, the answer is surprisingly simple in concept at least. You don't force it to rely purely on its memory. Instead, you give it an open book and tell it to check its facts. And this brilliant approach is called Retrieval Augmented Generation, or RAG for short. The open book test analogy is perfect here. Instead of a closed book exam where the AI just has to remember everything it learns during training, RAG lets it look up the answer. Before it even generates a response, it gets to retrieve information from a trusted external knowledge base. So here's how it works in a nutshell. You ask a question. The system's first move isn't to answer, but to go find relevant documents or facts from its knowledge source. Then it takes your original question, plus those facts it just found, and gives all of that to the language model. The result? A much more grounded, fact-checked answer. And if you break it down, this whole thing really has 5 basic steps. First, it figures out what you're asking. Second, it goes and retrieves the relevant info. Third, it adds that new info, that context, to your original prompt. Fourth, it generates the answer based on that combined info. And fifth, you get the final, much more reliable output. And this right here shows you the power of RAG perfectly. On the one hand, without RAG, the model just kind of throws its hands up and says, sorry, I don't have current info. But with RAG, it goes out, grabs these specific relevant chunks of text from its knowledge base, and uses them to build a really detailed, accurate, and up-to-date answer. It is a total game changer for getting reliable results. And really, that's the bottom line. By grounding its answers in real-time, verifiable data, RAG is a huge leap forward in making these incredible AI tools more reliable, more accurate, and, most importantly, more trustworthy for all of us. So, think about this journey we've been on. From teaching a machine what a single word means, to understanding the context of a whole sentence, to now giving it a library card to check its own facts, it just leaves you wondering, with this incredible new power, what kind of story will it write next?